So the next question we would want to ask is, well, how do you find that solution? How would you find it if you didn't know it? And in some cases, an analytic technique is possible for solving when the equation is called a separable differential equation. One of the first models that we saw where we didn't actually know how to solve it was the ELK model in our previous lesson, where dy dt equals 0.2 of y. And basically this just meant that the ELK population was growing at a rate of 20% per year, or another way of saying it is that 20% of all ELK reproduced. Another way of saying that is for every one female adult ELK, 0.2 additional ELK were born on average. Now here we can state that c equals 0.2t is a solution, and this can be justified in the same fashion as this exponential was a solution to this equation, but the question is, how do we find it? Now, we are going to define that if you can take the right-hand side of a differential equation and you can factor it out into two separate factors, one of which only has t in it, and the other of which only has y in it, then we call that equation separable. And you can see that now you've separated the variables from one another. Just to be super clear here, when we're saying g of t, think about g of t as a playground. And on the g of t playground, the only people or kids that are allowed on this playground are ones that at most depend on t. So if e to the t came along and said, hey, I want to come into the playground, we would allow e to the t into that playground because, of course, e to the t only depends on the variable t. If t squared came around, we'd say, yeah, come on in. You only depend on t. If 3, the constant 3 came around, we'd also let that constant in because g of t means that at most, that function can have a t in it. It can be a constant function. Any function can be constant and still be considered a function of t, but the second you throw y into it, it's no longer allowed on that playground. So if y squared t came around and said, hey, I want to come in, and say, nope, we can only allow functions of t. Kind of a silly analogy, but I find that works. Same kind of thing goes for h of y. h of y, we're only going to allow functions that depend on y into there. So, well, for example, if y cubed came along, you're welcome to come in. If sine of y came along, you're welcome to come in. If 7 came along, we'd allow 7 into that playground. So when we say separable, one of these functions could be a constant function. And to quickly look at this, let's look at a couple of examples of, is dy dt equals 3t plus 1 times y squared separable? Well, clearly it is, because it's already written as a product of two factors, one of which is a function of time, and the other of which is a function of y. And so I can say that g of t is 3t plus 1, y squared is h of y, and it clearly follows that form. It can be expressed in that form, therefore it would be called a separable equation. Some equations, like number 5, are not initially written in the form that we like. So we sometimes have to massage it a little bit to see if it's possible to get it in the correct form. In this case, I see that both terms contain a y and a t squared. So if I factor out say a t squared, or a y, doesn't really matter which, then I could say that t squared times y minus 6y is now a function of two components, a g of t multiplied by an h of y. Alternatively, another way you could have written that, and these are not unique, meaning sometimes you could have, like if I had factored out a y instead and written this as t squared minus 6t, notice that the factorization is different. In this case, I would have called g of t, t squared minus 6t, and h of y would have just been the function y. In number 6, we don't even see a y in it, and that's a good sign. Now this is something you could solve just by using your standard Calc 2 integration, because only the independent variable comes into play. But here's one fun thing you can do, and most people find this kind of mind-blowing at first, but what if I just factor out a 1? I just factor out a 1 like this, which is still a true statement, it's still the same equation. Now, based on our playground analogy, we could say that this is g of t, and we could say that this is h of y. And so our h of y is a constant, our g of t is actually a function of time. So this one is indeed separable as well. Same kind of thing goes for number 7. In this case, I don't see a function of t, but if I write this as 0.2 times y like this, and the parentheses are just there for emphasis, they don't need to be there, but this I could call my g of t multiplied by my h of y. You could actually, another way to do this would be to say, well, I'm going to write this as 1 times 0.2y, and in this case I would claim that g of t is a constant and that h of y is the function 0.2y. So again, these are not unique factorizations. Sometimes there's more than one way to do it, but as long as you can write it as a product of a g of t and any h of y, you're in good shape. Number 8 is a little bit disconcerting because I see this plus 1 here, and that's throwing things off. So I can't factor out a y, I cannot factor out a t, therefore this one is not separable. It is not a separable differential equation. So I just cannot write it, the first term is written as a factor of t and y, but I've got to be able to do it to the entire right side of the equation, as we see here.